In this lecture, I'll give a very brief overview of organic intermediates. In the following lectures, we will look at the specific intermediates and their reactivities. But in this lecture, we will just give a brief overview of each. But first, we will give a definition of reactive intermediates, and we will then look at the different interactive intermediates. Most we have seen from undergraduate organic. These include the carbocations, radicals, the anions, and carbenes. Before we start, however, let us look at a specific type reaction that we covered in undergraduate organic, and that's the concerted reactions. So we have here the E2 elimination, bimolecular elimination, and the SN2, which is bimolecular substitution reaction. These reactions are examples of organic reactions that occur in a single step. Notice here the key word is a single step, which means that there are no intermediates. So for these type reactions, there are no intermediates. They are described as concerted reactions. As we know in chemistry, we often communicate by using diagrams. And here is the energy profile for a concerted reaction or a one-step reaction. In this case, we have the reactants and it's going to the products. So here's the reaction coordinate or the reaction progress going in that direction, and the energies of the reactants and products are shown here. So here we have the reactant, and in a single step it goes to a transition state and onto the products. Notice the transition state is not an intermediate, it's just a description of the bond breakage and bond formation of that step of the reaction. And if the reaction is a one-step reaction, there's only one transition state. As you may recall, this gap here is the energy of activation, and this gap here is the enthalpy of the reaction. In this case, this is an exothermic reaction because the reactants are at a higher energy level compared to the products, which means that heat is given off. But let's look more now at reactions that occur in which intermediates are formed. So let's look at this general reaction. Reactants going to products. Typically, intermediates are formed as the reactants are transformed into the products. And of course, we have here different steps that occur to form each intermediate. Remember again, a reaction mechanism is a step-by-step description of a reaction. So here is essentially the reaction mechanism for this reaction. Here's one step, here two steps, and three steps. So this is a three-step reaction as described here. One step is the rate determining step, or the RDS, which is the slowest step of the reaction. And that slowest step of the reaction gives the overall rate of the reaction. The other steps that are not the rate determining steps are described as fast. So just to recap, a reaction goes from reactant to products. For most reactions in organic chemistry, it occurs in different steps and different intermediates are formed. So here is just an illustration of the intermediates that are formed, 1, 2, before the products are formed, and here are the steps, K1, K2, and K3. So, as we said earlier, a reaction mechanism consists of step-by-step description of that reaction. Notice it's a step-by-step description. So in your undergraduate course, you were asked to write a mechanism, which is basically a step-by-step outlining the different intermediates that are formed for each step. So let's look at the different type intermediates that are formed and type examples of the type reactions. For the E1 and the SN1, you may recall the E1 is unimolecular elimination reaction, and the SN1 is a substitution reaction, unimolecular substitution. For these type reactions, carbocations are formed. So those are the intermediates that are formed for these type reactions. And of course, as you will recall, the stability of carbocations are tertiary, more stable than secondary, more stable than primary, and more stable than the methyl. So the tertiary carbocation is the most stable carbocation, and the methyl carbocation is the least stable. Another type reaction that we looked at was the halogenation of alkanes using either chlorine or fluorine. For those reactions, radicals are formed as intermediates. And again, the stability of radicals is that the tertiary radical is more stable than the methyl radical. Another type reaction that we looked at was the Aldol condensation. For these reactions, the enolate or the anion, which is an example of an anion, is the reactive intermediate. You may recall also that we have the reactions in which a alkene reacts to give a cyclopropane, and one specific example is the Simmons-Smith reaction, where alkenes are transformed into cyclopropanes. The reactive intermediate for those type reactions are the carbenes. So these are the 4 type intermediates that are typically formed for organic reactions, and throughout this course we will study these intermediates. Let us look at the energy profile or the reaction coordinate for a typical reaction here that occurs in which intermediates are formed. So here's the reactant and here's the product. And of course the reaction progress goes in this direction. So we have the reactants. In the first step we form a transition state and it goes to an intermediate. Notice this is an intermediate here, not the product. So that's step number 1. Then in a second step it goes on to give the product. Just to refresh your memory, the transition state is right here for that step number 1. The transition state here is for step number 2. So for each step in the reaction, typically called elementary steps, there is a transition state for each step. will recall also that the energy of activation is right here for that first step. And of course, here is the enthalpy for that reaction. Let's look at the black compared to the red. Here you can see that the energy of the intermediate formed for the black trace is less stable than that formed for the red reaction path. As you can see here, this is lower in energy, more stable, and this is higher in energy, less stable. So this would probably represent, if it were an E1 type reaction, a tertiary or more stable carbocation, and this would represent your secondary or less stable carbocation, which goes on to product. I just want to emphasize here, or to point out here, that we have two products that are formed. One is less stable and the other one is more stable. These are called the thermodynamic products, but we'll get more into that later on. So the take-home lesson from this plot is that it's possible to form different intermediates that are of different stabilities as we propose mechanisms, and we can reflect that difference in stability using the energy profile or the reaction coordinate diagrams. Okay, so you will recall in your sophomore organic, no real evidence was given to prove that the intermediates given in a mechanism were the actual ones. In other words, for the E1 or the SN1, you were told that the intermediates formed were a carbocation, with no experimental evidence to say, well, gee, this is a carbocation with a positive charge. In this course, we will be concerned with real experimental evidence and other type evidence, calculations, for example, and using different tools to determine the nature of the different intermediates. So in other words, instead of saying that for the E1 mechanism, the intermediate is a carbocation, we will present experimental evidence to demonstrate that the intermediate is really a positive, a carbocation, and not a carboanion, for example. These evidence or experimental information that we'll use include the kinetic isotope effects and linear free energy relationships. That should be pluralized. So we'll look at these in great detail throughout the course. In the latter section of the course, towards the end of the course, we'll apply these tools to determine the mechanisms of a wide variety of reactions that we will read or we will find in the literature or the publications. So let us do a quick summary here of one type reaction. Here is the addition of HCl to methyl cyclohexene, adding HCl to the double bond here as an addition reaction. As you can imagine, the products are here, two products, because they can add both ways to the double bond. The first step involves the protonation of the alkene from the acid. So here's the acid, here's the alkene, which is nucleophilic. Electrons, pi electrons, will interact with the partial positive of the acid to give intermediates. So this is step number one. Notice two types of carbocations are formed, a tertiary and a secondary. So if you were reflecting on the energy profile, this would be lower in energy, more stable, and this would be higher in energy, less stable for the intermediates. Notice these are intermediates. This is the formation of first step of the reaction. In the second step of the reaction, as you can imagine, the Cl- reacts with the carbocation to form the product. Same here. Cl- reacts with the carbocation to form the product. You'll see here that this is the major product because it's formed from the more stable intermediate, tertiary carbocation, and this is the minor product formed from the less stable carbocation. So here again we have the stability of carbocations, in which the tertiary is more stable than the secondary, than the primary, and far more stable than the methyl. So the methyl carbocation is the least stable, and it's not very stable. So let's look at, well, the reaction profile. So here's the secondary carbocation compared to the tertiary carbocation, more stable, lower in energy. So here's the first step for that formation, secondary. First step for the formation of the tertiary. The tertiary goes on to form the product, and the secondary goes on to form the product. Again, the same information can be obtained from this type diagram. Transition state for the first step, energy of activation for the first step. You'll see that the energy of activation for this first step here is pretty high compared to the energy of activation for the second step. Hence, this step here is the rate determining step, and this step here, because the energy of activation is so small, is a fast step. So now you can see the different steps of a reaction mechanism, step-by-step description, and the slowest step is the rate determining step for that reaction. Let us look at another type reaction we looked at, and that is the halogenation, which would be the chlorination or the bromination of alkanes, hydrocarbons. Here, for example, chlorine reacts with methane in the presence of heat or light to produce the organic product, chloromethane, and HCl. So that's the overall reaction. Here's another one. Cyclohexane, a hydrocarbon, reacts with chlorine in the presence of heat to produce chlorocyclohexane and HCl. That's again the overall reaction. But what is the mechanism for these type reactions? As you will recall, the heat or light breaks the Cl-Cl bond in a homolytic manner to produce radicals. These are chlorine radicals. In the second step of the reaction, the chlorine radical abstracts a hydrogen atom to form HCl and a methyl radical. So that is our organic intermediate that's formed for this reaction. Of course, it goes on until we actually get the product. So these are different steps here for the reaction mechanism. Different elementary steps or reactions for the overall reactions. You will recall that they have, for this type mechanism, their names: initiation step, propagation step, where more radicals are produced. And here's another propagation step. Radical produces another radical. And a termination step, where radicals are terminated by coupling or coming together to form a neutral product. Here's another reaction, and this is the Aldol condensation. For this type reaction, the enolate or the enolate anions are formed as intermediates. So as you can see, we have here acetophenone reacting with the base gives this as the product. The mechanism, however, involves the base abstracting one of these hydrogen as a proton, notice as a proton, to form water, and what's left is the organic anion. Since it's adjacent to a carbonyl, it's called the enolate anion, but it's an anion, it's a carboanion, and this anion reacts with another mole of the ketone to form the product. So again, this is the mechanism for the aldol condensation. Here's an example for crossed aldol condensation, where we have acetophenone as shown here, base reacting with one of these hydrogens as a proton to create the enolate intermediate, which is an anion, as you can see here, a carboanion, and this carboanion reacts with the carbonyl carbon of another molecule such as benzaldehyde to form the product here, which is the aldol product. It's called a crossed aldol because the enolate is different from the reactant. And here is another type intermediate that's formed here. You may recall again that if you have an alkene, carbon-carbon double bond, it can be transformed into a cyclopropane. The intermediate that's formed here, or that's used, or that's part of this reaction, is the carbene. The carbene. So here's the structure of a carbene. There are two types of carbenes, as we'll see when we get more into the details of these lectures. One is called the singlet, and the other one is called the triplet carbene. This is the singlet carbene, and here's the reaction to give the cyclopropane product. So here's an example. This is the Simmons-Smith reaction, where we have a carbene as the intermediate. It's actually described as a carbenoid intermediate because the actual physical carbene isn't formed, but pretty close to the carbene, and it's formed from diiodomethane reacting in the presence of zinc copper to give that carbenoid or carbene type intermediate. Reacting with the alkene gives the cyclopropane. Notice the name. It's a bicyclic system, so hence the name here. Here's another reaction. The alkene reacting with the reagents here that will generate the carbene or the carbenoid intermediate to give the cyclopropane here from the alkene, and these reactions are known as the Simmons-Smith reactions. So I think this is the end. Yes, it is. So these are the type intermediates that will be covered in this course. So what we'll do is we'll provide evidence that they really exist, and in addition we will provide evidence of the structure and charge of these intermediates. And towards the end of the course, we will utilize these intermediates as part of our reaction mechanisms, or the reaction mechanisms that are proposed for different reactions that we will find in the literature and also in our textbook. So once again, just review your undergraduate organic chemistry for the different type reactions and the intermediates that are formed, and I will put out another video shortly starting with radicals. So we'll look first at radical intermediates and reactions that proceed in which radicals are the intermediates. Okay? Okay, bye.